Running computer audio. So this video is going to be a little practice on some of our newer topics. I think I'll not do the slope field, but get some of the other things that we've been looking at just briefly in front of us, because the only way you learn math is repetitive considerations, and can't get repetitive considerations unless you do things early, and then you repeat often. All right, so we got inverses. We looked at inverses. F of g of x equals x, g of f of x equals x. For instance, a 3, I could cube a 3, get to be 27. I could take the cube root of 27, it comes back to 3. Or I could take a 3 and take the cube root of 3 and then cube it, and it comes back to 3. So that's kind of your formal definition of an inverse. If both of those things are true, then you got some inverses. Well, our inverses, we're not going to state the inverse explicitly. We're going to look at the relationship, and we're going to talk about finding g prime of 28, for instance. And we're going to say that f and g are inverses. Okay, so inverses, and x gets you a y, and then the y gets you an x. And we switch the x's and the y, and we solve for y, and then you got yourself a new function in terms of x based on inverse operations. All right, so a 28 here gives us some y value. But that y value is actually the input over here. So this is the input on this side, which means it's the output on that side. And we can't state the inverse of that explicitly at the moment. So the question is, counting on your fingers, what happens here? Well, we can see that a 2 gets us a 28. And if a 2 gets us 28, we know the derivative of this is 3x squared plus 10. If I drop a 2 in there, it looks like I got 22. So f prime of 2 is 22, and I'll put that over 1. Now remember, this is an expression of slope at the instant when x is 2 on this cubic function. So slope, y2 minus y1 over x2 minus x1. And keeping in mind that we switch the x's and y's means that the slope of the inverse is going to be x2 minus x1 over y2 minus 1, or stated differently, a reciprocal relationship. So I now know over here that if a 2 gets me a 22, then g of 22 gets me 2, and I know that g, what did I say, 20? G prime at, a 28, a 2 gets me a 28, then over here, a 28 gets me a 2. Okay, got mixed up there for a second. And so g prime of 28 is going to be the reciprocal relationship 1 over 22. And you can see it easily with x squared, 3 gets you 9, derivative of x squared, 2x times 3 is 6 to 1. Over here, the square root, 9 gets us 3. And remember, the square root derivative is 1 over 2 root x. We drop a 9 in there, and we can see that we're over here going up at 1/6. So I think you can see all the kind of the switching of x's and y's here. So 3, 9, 9, 3, 6, 1, 1, 6. Okay, so hopefully you can trust that. All right, now we're going to do some volumes of revolution. Go Che Guevara. I think he invented this. It was definitely a revolutionary. All right, so we've got ourselves. Let me see if I can just manipulate my lanyard for a second without knocking the glasses off. Okay, I got it done. All right, so here's a radius. That's going to be a radius in this case, because we are going to rotate that radius around the x-axis, and it's going to carve out a little disc, a little circular disc. We used to play those in the, let's see, I started with a Walkman, then I missed the disc players. That's before your time. Anyway, so, it's one of those things that spins around. You put a needle on it, makes music. Here we go. Big R. Rotating around from 0 to 9. And that gives me one, what we call cross section. And that one cross section is circular with a little bit of thickness. So we got a pi r squared. That's the area of the circle. And then the thickness is in this case, it's going to be a dx, right? Because we're going to name our altitudes in terms. That altitude y is coming from whatever x value this is, whatever x value that is, I take the square root and that gets me that altitude. For instance, the square root of 9 is an altitude of 3. If x was 4, then that's an altitude of 2, so on and so forth. Okay, but the actual Riemann sum aspect of it, nobody ever calls it a Riemann sum, but I like to, because I'm hoping that you can see that this is a strip of area, dx square root of x, right? And that's going to be the area, but we're going to rotate the area all the way around the x-axis. So we're going to do that from 0 to 9. What is pi constant? So usually the textbooks place it outside the integral symbol. And then we have r, big R is square root of x. And so there's your pi r squared dx. And what we've created is a, just a, what? It's solid. It's a solid, and it's kind of looks like a, oh God, one of those Crusaders helmets, right? Back in medieval times, one of the knights helmet, and be solid. All right, so we could do the same thing over here, different shape. Maybe we get a megaphone out of this one. Bit of a megaphone. We got y equals x divided by 3. So you rotate that around the x-axis. And let's see if you can pause the video and do that. All right, so it's still a 0 to 9. We now know we take our pi outside. In this case, my r is defined by x over 3. So there's your pi r. We got to square that to get the area of the circle with a little bit of thickness. Now, if we put the two things together, we put those two things together right there. And all we wanted to do was rotate this area around the x-axis. Then we'd have a lot of empty space here. Empty space. Yep, and it would look something like this, I guess. Right? That would turn into a bowl. I guess if we rotated it around, we'd have ourselves a nice little bowl. Kind of a vertical one if we stood it up. All right, so where are we at? So what we're really doing is subtracting. I think you can see all of that. Yeah, let me tip it up a little more. Yeah, I mean, all we're doing is taking this, well, I constructed it before, but we're taking that away from the outer. So we could call this the outer edge, and this is the inner edge. Okay, and the way we do this really is, we got our big R, which we did before. That was the square root of x, and our little r, that was x over 3, right? So we could combine these into a single integral, so we don't have to write quite so much. So the dx is kind of a common factor. So we're gonna put that outside here, and then we're gonna take that 1, which is x over 3 squared, and I think we have it now. So we got something that is really in the form of integrating big R squared minus little r squared, parentheses dr, with a pi, a to b. That's generally what we're doing in this situation. Okay. And we can do integration with respect to y, instead of adding up chunks from left to right. We add up distances. We work with distances and things vertically. So let's say that we wanted to go from 0 to 10, and we wanted this area. Well, there's two ways you could do it, right? We could find square root of 10 here, I guess, huh? Square root of 10 squared is 10. So we could do it horizontally, and that's got a top minus bottom to it. And might as well do it real quick since we're talking about it. So what's the top? Top is always 10, height of 10. And the bottom, we're taking away this y value from 10, and that y value came from x squared. So it's just top minus bottom, integrate dx 0 to root 10. And we're not doing any rotations here. What about the area? If we wanted to do it in terms of y, it'd be the same area. And so we would work with horizontal chunks, which have dy vertical widths, and that is an x distance. But what does that x distance come from? Square root of y, right? So a minute ago, we said this was root 10, right? That's an x distance. And so if I take the square root of y, well, that's y right here, that's 10. Then that last chunk is a distance of root 10. And we would be adding up from 0 to 10 these x values, which are the square root of y. And, you know, it's right minus left, that's 0. So that should do it. Now let's actually rotate this around the y-axis, which is what I was originally going to talk about. Hopefully I'm not making any whopper mistakes here. Any big mistakes. So we're going to call these x distances square root of y. And we're going to go up to a height of 10. So we're going to rotate this way now. We're going to rotate this way around and stack from 0 to 10. So we're back to pi, 0 to 10. Those x distances come from this, but it's going to be pi r squared because we're going to get this circular rotation. So it's going to be the square root of y, which is that x distance, which we're thinking of as a radius. And we're going to square that dy. And that's going to get us another bowl. Okay. But what happens if we want to rotate that area around some other axis? So what we're getting here is practice constructing things. All right, so what do we have? We have an outer edge and we have an inner. And we're going to rotate the inner around and take it away from rotating the outer. So let's just get the outer. Well, the outer has this for a radius. Looks pretty constant to me. Looks like it's just 10 units. So I guess we got a pi, and we're going to go from, we're rotating dy. So dy is going to go from 0 to 10. We're going to stack these radiuses vertically. Okay, so that's the outer. That's the pi r squared, excuse me, pi r squared dy gets us a kind of a solid that looks like a can, pretty wide can. I don't know what comes in those kinds of containers, but maybe you can think of something. And now we're going to take away, for empty space, we're going to take this empty space away. So we know our right-hand border is 10. The question is, how much do we take away? We got to take an x distance away in order to make that our little r. Well, where does that x distance come from? Square root of y. Been working with it, right? So 10 minus the square root of y, which becomes right minus left. We're going to go right to that spot, right? We're going to take this away from 10. I'm going to take that x distance away. And that's going to give me little r. So that's going to be minus, in parentheses, 10 minus the square root of y, pi r squared. And now I think we've captured what will become amusement park ride, maybe. I don't know, you're sitting down, swinging around, getting your stomach all in knots. And I guess that would look like that over here, swinging it around. Yep. So that's another volume of revolution. We'll do it in terms of x this time. We'll go back to what we did a few minutes ago. You know, we're kind of familiar with this graph, I hope. And so now we got big R. Let's see if we got some red in here. Oh, look at that. Big R, little r. All right, so we got to have ourselves an A to B. Over there it was C to D. Pi, we got to have our big R squared minus our little r squared dr. So what do we got? Well, we know that was a 9,3. So we are definitely going to do it in terms of x, which means we're 0 to 9. Oh, yes, 0 to 9. Okay, 0 to 9. And we need big R. Well, big R has a top number, which is generated by plugging in some x value. For instance, if I put a 1 in here, then that's 1 unit plus the 10. That's 11 units long. How do we get it? Top minus bottom. Can't go wrong, and you don't have to think. What's the top? The y values are coming from the square root of x function. That's r. When I top minus bottom, what's the bottom? The bottom's minus 10. And I hope you can see that minus and minus 10 tacks on those 10 units of length, plus the square root of x. Okay, so there's your pi r squared minus Now we got to do the same thing for, actually get another parentheses in there. Same thing for little r. Well, little r has a top, it's the inner edge. For little r, the inner, this is the outer edge of our volume of revolution. So the inner edge comes from those y values. These are y values, come from taking an x and dividing it by 3. So if we took this x and divided it by 3, we'd have a height of 3. So the heights are increasing at a constant rate here. And so what's top minus bottom? Top. X over 3, bottom, minus 10 squared dx. And that's all you got to do for me, JTC. Just the calculation. That's what you'll be doing on your tests. All right, they're awkward to start, easy to make mistakes, easy to lose your concentration. But with sufficient practice, we'll probably get pretty mechanical with those. And the ones that the College Board will ask you might be, we might have to use some calculators to find points of intersection and get good with the technology. And I'll be counting on you folks to do a better job with that than I will. But we'll sort that out after midterm. Volumes with known cross sections. All right, so what's a known cross section? Circles, right triangles, semicircles, squares, rectangles. Let's do a rectangle. Here we go. I just folded this paper. It's got a dx, right? Because it's side to side width, and it ain't a big width. So it's got that. Looks like the base, looks like the height is maybe 4 times the base. Let's see. 1, 2, I'm going to go 3 times. Okay, so that height is 3 times the base. And the language is a little awkward to start. So the language in the textbook would say, find the volume generated when cross sections cut perpendicular to the x-axis. They might have said, find the volume of a solid whose cross sections form rectangles, whose height is 3 times the width, and the width is cross sections cut perpendicular to the x-axis form these rectangular creations. So here's one. Okay, so I'm cutting like a loaf of bread, a slice of bread, and that slice is perpendicular to the x-axis, just like your trig. Okay, in your trig, what do you do? In your trig, you draw a triangle and you draw the altitude perpendicular to the x-axis. Okay, so that's what we're doing here. Now, that's where this one would be. If I was to the left, I got to really make this smaller. Let's see if I can do this on the fly. Smaller. And if that's smaller, then the width has to be smaller. There we go. Not too bad. Not too bad. Okay, and then I got one further to the left. And obviously I have to open things up. So what are you creating? If you can visualize it, it's hard to visualize. There's this tapering as we move from right to left. So kind of a lean-to, a solid lean-to. And I don't know, I think if you get on YouTube, you probably can see some computer graphics that do justice to this description. All right, so let's actually write the calculation. Okay, I don't think rectangles have anything to do with pi r squared. All right, so we said the base, the height was 3 times the base. So the base is b, the height is 3b, but we're going to work with x, of course. And my height, my width, this is the base. The base is x over 3. So the base is, that width is based on some x value divided by 3. So this one, of course, would have been 9 divided by 3. That would have been 3. And coming out from the wall would have been 9 units because we said that the height was 3 times the base. All right, so we got x over 3 times x over 3, which is x. So if I integrate this from 0 to 9, boom, boom, dx, I'm done. That would have found that volume of that whatever shape was generated from those rectangular cross sections. All right, hope that becomes better understood as we get some practice. Repetitive considerations. So equation line tangent to arc sine of x. So y prime, this is one of the ones we're starting every class with, I gather. So arc sine, remember, is the right half of the circle that forms an arc. And we have the ratios from -1 to 1. And over here, we have all those angles, 90 degrees, 60 degrees, 45, 30, 0, -30, -45, -60, -90. I know we did a lot of practice in my pre-calc class. I don't know how much you did. We did a lot. So I'm hoping that's familiar to those kids. And we'll see. If you didn't get much practice with arc sine, well, we'll fill in those gaps going forward. So y prime, if y equals arc sine of x, arc sine of f of x, excuse me, then we've got f prime of x over the square root of 1 minus f of x squared. So in this particular case, the derivative of x is 1, and that's the square root of 1 minus the function is x, so x squared. All right, so what's an easy one to start with? How about x equals a half? All right, so we got ourselves our triangle. The sine is a halfway up. There's that and that halfway up. We don't care about this one. We're on the arc. So we got the altitude. You got the ratio. So what is this asking? Hey, I'll give you the ratio. You give me the angle. So what was the angle? Pi over 6. So 1/2 gets me pi over 6. All right, so we got x minus a half plus pi over 6. There's your a and b, your x and your y, your output. Now we need the slope. We got a formula for slope. We know our x is a half. So 1 over the square root of 1 minus 1/4, which is 3/4. 1 divided by the square root of 3/4. 1 divided by root 3 over 2. So that becomes 2 over root 3, which is roughly 2 over 1.73 as a, so it's a little bit bigger slope than 1. I'm sorry, a little smaller slope. Yeah, that is bigger than 1. That was confusing. This is smaller than that, so it goes in more than 1 time. Okay, so that's our slope. 2 over root 3. And that's our ELT. Okay. Yeah, it's when we start integrating these that it gets a little more complicated because there's a lot of things that kind of look like, is it an ln? ln puts, things in the denominator. Is it a square root that ends up in the denominator? So does arc sine, so does arc tan. So it really comes down to experience. How do you get experience? By finishing the course before midterm so you can practice it every day the rest of the year, or at least till Christmas. All right, so now we're going to do arc tan. 2 more problems, then I'll upload this. And hopefully you get some practice with it. Arc tan, all the same kind of discussion. It's the same arc, right? But the ratios go from positive infinity to negative infinity, right? And 90 degrees is actually undefined. So I suppose I should put some open circles here. Why is 90 degrees undefined? Because the height is 1 and the width is 0. And the height over the width is your sine over your cosine. So what do you got? You got 0 degrees and 45 degrees. Those are the most famous. They're the easiest to work with. The arctan of 1 is 45 degrees, and the arctan of -1 is -45, right? So I shortchanged the negatives here. I apologize. I discriminated against the negatives. And I've been at this a long time, so unforgivable on my part. Arctan of x. Arctan of x is derivative y equals 1 over 1 plus x squared. That's the arctan. Unless my memory, has faltered, that's what it is. And it could falter at any time. At any time, I'm ready for the nursing home up in Vernon. So if you don't see me in class tomorrow, you know where I am. All right, so we got y prime equals 1 plus 1 over x squared. Let's do at x equals, look at that, dyslexia. My God, so let's get something over here. It's best to study tangents, not with the unit circle, not with the root 3 over 2, 1/2, 1, but doubling the size of that. 1, root 3, 2. Much easier to talk about tangents of 30, 60, 90s when you double the size of the triangle. So here we go. Arctan of root 3. Okay, I give you the ratio. It's really over 1, but you wouldn't have to put it over 1, right? So I'm giving you root 3. What's the ELT at root 3? Well, I think we're looking at a pi over 3 here, 60-degree angle. So we got x minus root 3 gets us the angle 60 degrees. And now we got to do what? We got to apply. We've got to put our x in there. The square root of 3 squared is 3. So 1/4. All right. And we don't generally graph arctan and arcsine that much. You're just inverting the x's and y's on the tangent function between -90 and 90. But there's your equation of your line that's tangent. Just a mechanical practice at this stage. We can do some graphing of those functions later. But we just want to get some mechanical precision going. And then we got the whole second half to talk about things. Here's the related rates, a different type than you've seen before. We were doing grandma and grandpa. Now we're doing the volume of a sphere. It's just a ball. Is changing at 8 centimeters cubed per second. Find the rate at which its surface area is increasing when its radius is 12 centimeters. All right, sounds kind of complicated first time you hear it, but how does the volume of a ball change? Drop it in a paint bucket, right? And what are you coating? Surface area. All right, so what is a sphere? Sphere is, let's see, how do I want to do this? Volume equals S 4/3, let's see, 4/3 pi r cubed, I believe. I think the volume is 4/3 pi r cubed. Yeah, memory serves me well. We've been through that a second ago. Hope I'm right. I'm not going to do this video again. All right, so volume equals 4/3 pi r cubed. So what's surface area? Well, if you had a ball and you were outside and it was, a misting, and then you had a mister, right? And every independently, it's changing like it was just freezing. As soon as that little mist hit the ball, it freezes. Well, the ball's growing in volume, right? And it's linked to its surface area. So its surface area is going to be the derivative of this. Okay, so if you multiply by 3, we get surface area is 4 pi r squared. Okay, now if we want to bring in, comparing it to time, we did a chart, time to radius to area of the circle, a couple days back, right? So we're going to do dividing by dt in a moment here. So find the rate at which its surface area is increasing. So we got to take the derivative of surface area. And so the derivative of surface area is equal to find the rate at which its surface area is increasing. Okay, so we got to take the derivative of this, which is 8 by our dr. There's a dr here with a dt. Okay, that's the 8 pi r dr dt. And so over here, we've got, God, why do I give myself these problems when my brain is tired? All right, so dv dt equals 4 pi r squared dr dt. Okay, and so we want to find r is given, it's 12. So 12 dr dt we can find here, I guess, first. So okay, so we got to find dr dt. So dv dt was given 8 centimeters cubed when the radius is 12. So that's 4 pi 12 squared. And this can get, so we can find dr dt. So we're going to divide this 8 by 4, 144 times 4. 400, 560, 576, I believe. 576 pi. I should be doing this and talking about the units too. Squared units divided into cubic units gets us linear units here. So 576 pi is equal to dr dt. Well, I hope I'm not butchering this because my brain is tired. So 8 pi when r is 12. When r is 12, we can substitute that now. We could substitute 576 pi for dr dt. None of those numbers are very unit friendly, but I think I did justice to the cause. But if I didn't, I'll fix it up in class and give you a better sense of how to do that problem, because I'm running out of gas here. All right, so that's just some practice. and we'll take it from there.